So let me give you here an example of a very well-known antenna, the dipole antenna. And here we can see a few of its properties combined together. So this is, as I mentioned before, a typical dipole. In this particular case, the dipole is actually being fed by a coaxial cable. So, and there's a transition at the end. So one part of the dipole you can see right here is actually connected to the ground plane of this coax. The other part of the dipole is being connected to the center conductor of the coax. This has a radiation pattern that looks more or less like a donut. The dipole here actually is sitting right here. So clearly you can see that along this axis there is zero radiation, and there is maximum radiation along this axis here. But of course the radiation is azimuthally symmetric. So as you rotate here, you will see, of course, exactly the same radiation everywhere. And in a two-dimensional pattern, you will see a dipole pattern more like of that nature. I already mentioned the directivities for dipoles, but the other thing I would like to mention here is that if you have a very small dipole that is much, much less than the wavelength, you will more or less get a sine theta pattern, which is the theoretical result for a Hertzian dipole, but your efficiency will be very poor. So that's actually the main example you can remember of why we're not using small antennas. So electrically small antennas, meaning antennas with electrical length much less than the wavelength, are fantastic from a form factor point of view because they can be mobile, but they're horrible from a point of view of efficiency. Sometimes that's the only thing we can do. For example, if you have an AM radio operating at kilohertz, you can't really get much of a half wavelength antenna there. Obviously, at kilohertz, such a thing would be humongous. So you're simply stuck with a small dipole, and you simply transmit a lot of power, and you work with an antenna that is very, very poor in terms of efficiency.